So we're going to look at the test review for test 3. So as you can see in these bulleted items, the things that you need to know for this test is the relationship between position, let me just get a different color here, the difference between position or the relationship between position, velocity, and acceleration. And you have a number of pages in your packet that have all those notes. You have several examples. And so make sure you understand things like the difference between average and instant, one being algebra and one being calculus, those concepts. On this test, you're going to need to be able to recognize the definition of derivative. Remember, there are 3 forms. The limit definition of derivative could be a general derivative, or there are 2 point-specific forms. So make sure that you go back and do some practice on those, and you'll see some of those in the review. You need to understand the relationship, I'm on the 3rd bullet, between a derivative and a tangent line, and you certainly need to know that the derivative is the slope of the tangent line. That's something you obviously need to know all the time. You need to be able to examine a function and identify the graph of its derivative. Actually, that's not on this test, even though it's on this bulleted item. This must be an old list, so I'm going to take that out for you. So that's gone. Definitely find symbolic derivatives. Remember, that's when you have an f or a g or an h, and you don't actually know the function, but you have to find derivative. There will be a focus on product rule and quotient rule. I need to know if you can perform the product and quotient rule, and I need to focus on your memorization of all 6 trig derivatives. Make sure you can determine the values where a function has horizontal tangents. The key to that is setting the derivative equal to 0. Horizontal tangents would be slope of the tangent line is 0, so we would simply set the derivative equal to 0. And for sure, examining a velocity or position graph and being able to answer questions, that really goes back to the first one, and understanding the relationship between position, velocity, and acceleration. So I'm going to work through these problems. I may not work them all completely out because I already have worked the problems and posted the solutions in your packet. This is more about how to read the problems, how to interpret them, how to break them down, how to set them up. So let's begin. In problem number 1, we have an s of theta. So in this case, my variable is theta instead of x. S of theta is 5 theta plus theta times cosine theta. So that's kind of interesting that that's multiplication. It represents the position of a particle moving along a horizontal line where s position is measured in feet and theta is measured in seconds. Letter A wants me to find v of theta. So that tells me I want instant velocity. I'm going to do it over here on the side. So I'm going to change that to white. So 1a, the derivative of position, so s prime of theta, you should definitely understand this, is equal to v of theta. So I'm going to come back to the position function that was given, and I'm going to find the derivative. The derivative of 5 theta, think of it as 5x if you're confused. The derivative of 5 theta is just 5 by the power rule. Now remember, hopefully your math eyes spotted a product right here. We have theta multiplied by cosine of theta. So over on the other side, I'm going to write down my 2 factors. There's theta and there's cosine theta. I need to perform the product rule. The derivative of theta is 1, just like the derivative of x is 1. The derivative of cosine theta, it's a co, so the derivative is going to be negative, is negative sine theta. So we're going to have the first times the derivative of the second plus the second times the derivative of the first. And because we're adding, order really doesn't matter. So I will have 5, and when I multiply negative sine theta times theta, I get negative theta sine theta, that's first derivative second, plus second cosine theta times 1, and that is my v of theta. That's my instant derivative of position, instant velocity, not average, instant velocity. Letter B wants me to find the acceleration function. So I'm going to change colors now to yellow. So right here in number 1A, I had the velocity. So now I'm going to do 1B, which wants me to find the derivative of this velocity function. The derivative of 5, of course, is 0. And again, right here, I have a product of negative theta multiplied by sine theta. So I'm going to go over to the other side. So negative theta, that's the first. Sine theta is the second. The derivative of negative theta is -1. The derivative of sine theta is cosine theta. So I'm going to have the first times the derivative of the second. So that's going to be negative theta cosine theta plus second times the derivative of the first, and -1 times sine theta. So that's actually going to be, instead of a plus, it's going to be minus. Wait for my eraser to pop up here. There we go. Minus sine theta, and that is my acceleration function. Instant acceleration, derivative of velocity. So remember, for acceleration, the second derivative of position is the first derivative, eraser again, come back please, there we go, is the first derivative of velocity is acceleration. So make sure you know those relationships. Moving on to letter C. In letter C, we are determining whether the particle is traveling to the right or to the left. Now, we talked about in class we could use the position function or we can use the velocity function, but if we were going to use s of theta, we would need a graph to actually look to see when the graph of position is increasing and decreasing. So instead, our second go-to in calculus is to use v of theta, because when we look at velocity, we really need to examine the sign of velocity. So the first thing I need to know, and I'm going to come over here and erase my work on the right-hand side because I'm going to do a lot of work over here. So let's get rid of all of that. All right, so first we're gonna set the velocity, instant velocity, v of theta, equal to 0, and that's going to tell me when the particle is at rest. And so if I set v of theta, which is, oh, wow, I was going to say, I never would expect you guys to solve that equation. They're giving me two particular values, and so I'm going to need to read. I need to know the if the particle is moving to the left or right at pi over 2 and pi. So I actually am not going to need to create the number line because I have specific values. I simply want to know the velocity at pi over 2, positive or negative, and the velocity at pi, positive or negative. So I'm going to substitute into velocity, which is over on my other side. So I have 5 minus pi over 2 times the sine of pi over 2. I'm just substituting pi over 2 into the velocity function, plus cosine of pi over 2. So now I have to know my trig value, so that's a warning. The sine of pi over 2 is the y value at pi over 2, which is 1, so that's going to give me 5 minus pi over 2. Cosine of pi over 2 is the x value at 90 degrees, or at pi over 2, which is 0. So this is 5 minus pi over 2, and if you're not sure what pi over 2 is, remember pi is 3.14 divided by 2 is going to be smaller than 5, so that's going to generate a positive number, and that's all I need to know. So the particle is traveling at pi over 2, the particle travels, I would write a better sentence, I just don't have space, to the right, and the important thing I can tell you now for your test is tell me why. Because v, now watch very carefully, precise and specific, of pi over 2, not v of t, not v of theta, v of pi over 2, we're only going to speak specifically for this instant of time, is greater than 0. And I'm not going to work out the next one, which is v of pi. It's the same thing. You're going to substitute, determine the sign, and make a decision. All right, let's, do I want to clear, let me decide whether I want to clear the screen or not, because I may need some of the stuff that I have here. So now we're looking at letter D, set up, but do not solve. Set up an equation that we could use to determine the values at which the acceleration function has horizontal tangents. Read this very carefully. I want to know, when does acceleration have horizontal tangents? So as soon as my eraser pops up here, I'm going to erase, oops, give me a second here. I'm going to erase my work on the right hand side, and we're going to have a conversation about what we have to think about to figure out when the acceleration function has horizontal tangents. So let's get rid of all of this over here. Oh, come on. Because I want to keep the stuff on the right-hand side, at least for now. Okay. So for acceleration, so I want to know when A of t, I don't have the graph, has horizontal tangents. Think, 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 think. That means, when is the slope of the tangent line 0? Well, if I'm talking about slope of tangent line is derivative. That's one of the concepts I said you really have to understand. So what I really need to know here is, when is the derivative of the acceleration graph equal to 0? Not A of t equals 0, the derivative of A of t. So the equation that I would set up would be A prime of t, which I'm not going to calculate, by the way. Maybe I will. We'll see how easy it is. I don't want to waste time. That's something we're not really going to need. Yeah, the acceleration function is in 1b, but I'm not going to find the derivative of that. So I would set the acceleration function's derivative, if I had it, if I were to find it, equal to 0. So that's the symbolic representation of what we're looking for letter D. Pay very close attention to that. I'm not setting acceleration equal to 0. Setting acceleration equal to 0 would be when the acceleration graph crosses the x-axis. I want the horizontal tangents of the graph. All right, moving on to letter E. So now in letter E, we're also going to set up, but do not solve, another equation that could be used to determine when the particle is stationary. So I actually kind of revealed that a little bit earlier. So first of all, stationary means at rest, and at rest means not moving. And not moving, here it comes, is when the velocity function v of t equals to 0. So if I wanted to bring in the velocity function, because I know what it is, and it said set up but do not solve, I could do 5 minus theta sine theta plus cosine theta equal to 0. And if I were to solve this and the directions did not tell me to solve, I could find the thetas when the velocity is 0, meaning that the particle is stationary, not moving. Okay? All right, now I think I can clear my screen because I know what's coming next. So I'm going to do a clear annotations. And let's go to letter F. In letter F, we're going to use function notation. So this is really all about your, do you understand how to find these things, but you don't really have to find them. Use function notation to indicate the following. Again, I can't stress strongly enough, pay attention to what I'm doing in these examples, because you're going to need to know all of this for your test. Okay? So here we go. Look at the words. It's all about reading. In the first one, I'm looking for instant. Come on, where's my pen? I'm looking for instant velocity. So instant velocity, here are all the different ways I could represent that. I want the instant velocity at theta equal to 7. So I could say S prime of 7. Or I could say V of 7. Both of those representations represent instant velocity at 7. The second one is average, the letter A, average algebra 1 velocity. And we talked about this in class. This is one that's easy to get mixed up. So let's think about average acceleration. Average acceleration, the literal definition of average acceleration is change in position over change in time. So the average acceleration is the position terminal, position at 8, minus position initial, position at 2. So that's change in position over change in time. And if I'm not sure, I can do my unit analysis, and back up at the beginning, it told me position is measured in feet, so that would be the units of the numerator. The time is measured in seconds, and so then I think to myself, does that make sense for velocity? Would velocity be measured in feet per second? And the answer is yes. The common error, so I'm going to do that way over here, and don't repeat it, don't even copy it down. The common error is to do v of 8 minus v of 2 over 8 minus 2. Now let's do a unit analysis there. The units of velocity in the numerator would be feet per second, and the units in the denominator, the 8 minus 2, is time, so that would be seconds over 1, and so the units would be feet per second squared, which is a measurement of acceleration. And I did not want average, so this is average. It is an average, but it's the average acceleration. Be very careful with that. Number 3, I want the location of the particle. Well, if I want location, I want the position, so that would be S of 3. So that's just a basic algebra expression. In 4, I want average, there it is again, average acceleration, and we talked about that. So if I want the average acceleration, that would be change in velocity. So really you're going back one function, so change in velocity over change in time, as I already wrote over on the side, v of 8 minus v of 2 over 8 minus 2. And you can see that I did the unit analysis on the other side, or on the right side. This is just a way to check, does it make sense that I have the acceleration? And yes, I do. Feet per second squared. In number, where are we? Number 4 we just did, except for it wasn't from 8 to 2, I apologize. In number 4, it was, let's go back to green, that was from 5 to 10, so this should be a 10, this should be a 5, this should be a 10, and this should be a 5. But really all we're doing here is setting these up symbolically just to make sure that we understand this. Lastly, number 5, your AP score is instant acceleration. That's easy. It's either the second derivative at 6, which is the same thing as the first derivative of velocity at 6, which is the same thing as acceleration. So make sure that you know that all 3 of those mean exactly the same thing. And the units here would be, as we've already determined, feet per second squared. All right, let's turn the page and see what we have coming up next. There you go. Words. Make sure you can read. Determine the slope of the line tangent to the curve. So slope of the line tangent, when you see that phrase, you should really just replace that with determine the derivative of the curve f of x. And now we got to play I Spy. I Spy with my little I. When I'm looking at this expression, hopefully you see a quotient. So we're going to need the quotient rule. So I'm going to do down d up minus up d down over down down. So I have down 5x plus 2, d up 3, derivative of up, minus up 3x minus 1, d down 5 over down down. Now, normally we would do some cleaning, but look at what the end game is here. The end game is to find the derivative at x equal to 2. Now the y value is irrelevant. This derivative calls for x. So I don't really have to clean this up because my final answer is actually going to be the derivative at 2. So I can just substitute 2 in place of all the x's. So I'm substituting a 2 here. So 5 times 2 is 10, plus 2 is 12, and that's times 3, minus, substitute a 2 here, 3 times 2 is 6, minus 1 is 5, and then that's going to be multiplied by 5. In the denominator, I'm going to substitute a 2 here. 5 times 2 is 10, plus 2 is 12, so that's going to be 12 squared. Simplifying, that's going to give me 36 minus 25 over 144. Yes, you should take it that far. And 36 minus 25 is 11 over 144. And so that's my final answer. And again, the reason I did not do any cleaning is because the end game was not to just find the derivative, it was to find the derivative at a specific value of x, so I wasn't going to do things that I didn't need to do. In number 3, what's going on there? Let's scroll this down a little bit. Reading, reading, reading is the important thing. If the position of a particle is represented by, so here's my position function. Ooh, I see a squishy product. I hope your math eyes see a squishy product. Determine the times at which the velocity, so I'm going to need velocity, is 0. Velocity, read, is, translate, 0. Velocity is 0. So I need to find the velocity, and as I said, squishy product, it's e to the t times sine t, even though they don't have those parentheses there to help us out. So here we go with velocity. So v of t, I'm going to do the product rule. I'll come over here and do my little strategy that I taught you guys if it's helpful. If you don't need it, it's okay too. So the derivative of e to the t is e to the t. The derivative of sine t is cosine t. So we have first, derivative second. So that's going to be e to the t, cosine t. The order doesn't matter because you're multiplying. Product is plus, so I'm going to come back over here, plus second times derivative first. Order doesn't matter. So I'm going to come back over here. I just want to put my e to the t first. Times sine t. Okay, so that's my velocity. Now I'm supposed to set that equal to 0. Now when you look, hopefully, I'm getting ready to set equal to 0 on the left-hand side. Hopefully you notice that I have a common factor of e to the t. So in order to solve this, I'm going to factor out e to the t. That will leave me with cosine of t plus sine t. And remember, we're setting that equal to 0. So if I have two factors, and that's what I have here, equal to 0, multiplied to make 0, either the first factor has to be 0 or the second factor has to be 0, and that's called the zero product property. Now, we know from Algebra 2 that you cannot raise e, there's no power that you can substitute and make e to a power equal to 0. That's never going to happen. So this is a bust. It doesn't get anything for me. So what I really need to figure out is when is cosine t plus sine t equal to 0? And there are a couple of ways to do that. I'm going to do it more like through an inductive process. We know that we have three special angles. We have 30, 45, and 60, or pi over 3, pi over 6, and pi over 4. Those are the special angles that we know. And it says here we're going to add cosine and sine to get 0. So we're looking for the family of the 30 family, the 45, or the 60 family. We need the family that has the same numeric sine and cosine. Now, you know, I'm going over to the other side, you know from your unit circle that the angle, so here's my x and y axis, you know that at 45 degrees, the cosine is root 2 over 2, and the sine is root 2 over 2. So this is going to be the 45 degree, or the pi over 4 family. Now, it can't be first quadrant because positive, positive. That would not make 0. Second quadrant, we have negative, positive. Ooh, opposite signs would make 0, so we're going to need the family member that is in the second quadrant. Third quadrant is not going to help us because we would have same sign. That wouldn't make 0. And in the fourth quadrant, we're going to have positive, negative. So we're going to need our second quadrant family member and our fourth quadrant family member in the pi over 4 family. So right here, watch, this is pi over 4, 2 pi over 4, 3 pi over 4. So one of my answers of theta, or t is equal to 3 pi over 4, or t is equal to, let's keep counting, this was 3, 4, 5, 6, 7 pi over 4. So those are the times when the velocity is equal to 0. Make sure you know your trig. All right, let me clear these annotations and I'm going to get that thing out of my way. So clear the annotations. And here we go. There we go. In the next problem, number 4, I think I'm probably looking at a derivative, but I'm not real sure. I hope I don't get tricked here. So this looks to me to be of the form limit as h approaches 0 of, it looks point specific. And remember, we're looking at, do you see what I see? And do you see what I see? And do you see what I see? All right, so over here, I see a c value of -1, a c value of -1, and remember, this is f of c. So this, if this is a derivative, notice I said if that's a derivative, it's going to be point specific. All right, so let's unpack that. So coming back over to the format, it looks like f of c plus h minus f of c over h. All right, let me see if I can decompose the function if this is a derivative. So I'm going to take the guts out of here. So that would be negative 5x squared plus, I'm going to take the guts out of this one, 2x minus 4. Now before I can declare that this is actually a derivative and not just a regular old limit, my c value, I'm believing that my c value is -1. I can uncover that by erasing. And let's make that smaller so that I don't. So there's the c value, -1. But I have to make sure that that c value produces a y value of -11. So I'm going to do a little check over here. So -5 times 1 squared plus 2 times 1 minus 4. So that'll give me -5 plus 2 minus 4. That will give me -5 and 2 is -3 minus 4 is -7. So that's not -11. So interesting. I have a feeling I meant for it to be, but it's not. Wait, I see an error. Yay. Well, I mean, not yay. I'm not happy that I made an error. I'm supposed to be substituting -1. So in here, this should be -1. This should be -1, okay? You probably already caught that. Good for you. So that would give me -5 minus 2. So that's -7 minus 4. Yes, is -11. Hopefully you caught my mistake. So what this represents in a complete sentence, this expression, the limit expression represents the, sorry, this is sloppy, the derivative, be specific, of -5x squared plus 2x minus 4 at x equals to -1. And now I'm going to evaluate that. So that means for me to find the derivative. So f prime of, I don't know why I said do not try to evaluate. You certainly can. F prime of x is equal to -10x plus 2. And f prime at 1 would be -10 times 1 plus 2. So that's negative 10. Why do I keep forgetting that negative? So that's going to be positive 10 plus 2. And so the final answer, this expression literally represents, I hate that word literally, represents the number 12. So the derivative of negative 5x squared plus 2x minus 4 at negative 1 is 12. Okay, is this the last thing or not the last thing? This thing, what we're going to do, it's not. This is really, really important, so focus. The graph below indicates the velocity, so I'm going to write that onto my graph. The velocity of a particle traveling along a horizontal line. Use calculus to complete the following. Write your answers as a complete sentence, justify with calculus. Now, I probably will not write complete sentences for number 1 time and number 2 space. So, letter A, on what intervals is the particle traveling left? So now I got to use my math eyes, which means I need to use my brain. So the question is, what do I think about for V of t for particle traveling to the left? I got to put it together. And hopefully you know that I'm looking for the sign of V of t to be negative. So if you look over here on the graph, the velocity function is negative in the purple region. Negative in the purple region. So everywhere I colored purple, velocity is negative. That's a book, by the way, and a movie. The particle is traveling left, so that would be from 0 to 2, open, comma, from 2, 3, 4, open, 5, 6, 7, 4 to 7, and the graph looks like it's stopping at 7, so I'm going to bracket that, and I'm going to say because V of t is less than 0, I could say V of t is negative. I don't have to say is less than 0. The velocity function is negative in that region. Letter B, when is the particle moving to the right? So this time we're looking for the sign to be of velocity. Let me be clear. Sign of velocity to be positive. So that would be in the orange zone. So in the orange zone, the particle would be traveling to the right from 2 to 4 because the velocity is greater than 0 or positive in that region. Letter C, particle stationary. Remember we talked a little bit ago, stationary indicates velocity is 0. And let me erase a little bit here. I can't tell if the graph is hitting 0 at 0 or not. I don't think so, and I think it is at 7. So 2, 3, 4, 5, 6, 7. So the particle is stationary at t equal to 2, t equal to 4, t equal to, I don't have any units on here, so I'm not including units. I don't see any anyway. 7, because V of t is 0. If you don't have any velocity, you're not moving. All right, traveling the slowest. Well, I think we just answered that. You can't travel slower than 0. So the answer to C is also the answer to D, because the slowest that you can travel is to stand still. Moving backwards is not traveling slower. The negative that would reveal that would simply be the direction, not how fast you're traveling. Letter F, to contrast that, if we're looking for when the particle is traveling the fastest, remember we are looking for the most extreme y value on V of t, the most extreme velocity. So our candidates are here, that's a low y value, here that's a high y value, and here is a low y value, and obviously that's the lowest y value. So this looks like it might be an estimation thing. Let me erase and see, because I've got my graph so messy that I can't tell what's happening. Yeah, that looks like it's going to be an estimation. So on a test, I'm going to try to stay away from estimations so that we can easily get an answer. So right there, if I travel up 1, 2, 3, 4, 5. So it's not quite 6. I'll just say approximately 5.8 or 5.9 or something like that. On a test, I will try to avoid times where you have to estimate those values. And then letter G is a really interesting question. They're all interesting. I love them all. So the last thing I'm trying to figure out here is, get a pen, go green. It isn't easy being green. On what intervals is the acceleration negative? All right, so we got to interpret that. Acceleration is the derivative of velocity. Derivative is slope. So acceleration is the slope of velocity, and we want negative. So when is the slope of the velocity graph negative? Well, the slope of the velocity graph is negative when the velocity decreases. All right, so let's look at that. We have a decrease, 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 decrease. Those slopes are negative. Think about putting your tangent line in there. Here, from the top to the bottom, or I should say the local max to the local min, slopes are negative. Think about putting your tangent line in, a decrease. So the acceleration is negative from 0 bracket to 1. It looks like about, we're going to call it 1. And again at 2, 3, 3, and we called it down there about 5.8 open because v of t decreases. Okay, let's go on and finish this up. I think this is the same. Oh, I guess number 6 is referencing that. Number 6, look at the velocity graph from above in number 5. So we're looking at our graph. This is still velocity. Use good calculus to notation to explain why v of t must be differentiable at t equal to 3. So here's 1, 2, 3. Why is there? Now we look right here. We know the derivative is 0. So because the slope of the tangent line, so here's my tangent line, slope of the tangent line is 0. So there is a derivative. Now, to explain why there is a derivative, we have to confirm that the left derivative, or the derivative, I should say, from the left, is equal to the derivative from the right. Now, we've had examples before where we sort of refute that the derivative exists, and we say that the left derivative does not equal the right derivative, but in this case, we're just going to affirm that. So we're going to say the limit as t approaches 3 from the left side of, and this function's name is velocity, so we're going to say v of t, there's y number 2, minus v of 3, that's y number 1, over t minus 3, so it's the function minus the, the function minus the y value, so y2, y1 over x2 minus x1 is equal to, left and right agree, the limit as t approaches 3 from the right side, y number 2 is the function, y number 1 is the point, or the y value there, t minus 3. So that is an affirmation. That's why we know that the derivative, why the function v of t is differentiable, does have a derivative at t equal 3. And last but certainly not least, number 7. Using the graph from number 5, so we're still back up. I was changing that to orange. Using the graph from number 5, which is up here, explain why there must, theorem coming along, be a value c where the velocity is equal to negative e. So I have to think about e. From my prior knowledge, I know in Algebra 2 that e is about 2.718 blah, blah, blah. Therefore, negative e would be approximately negative 2.718 blah, blah, blah. Or is it 217? I think, yes, it's 217, not 271. Either way, anyway, it's less than 3. Okay, so it's 217. Sorry about that. On the interval from 2 to 5, so there's a closed interval, write your answer using complete sentences. So I'm going to come up here to the graph. First of all, I'm going to clear my annotations to clean up my graph. Clear the annotations. There we go. And I'm going to go from 2, so that's not 2. Poopy, I went to the wrong flip chart. There we go. So 2, 3, 4, 3, 4, 5. So I'm blocking off the graph, and I see a function that is continuous. The velocity function is continuous from 2 to 5, so I condition met. I'm looking for a specific y value, and my only y value theorem is intermediate value theorem. So I'm trying to affirm that. So I'm going to begin by stating v of t, specifically not the function, not f of x, is continuous on the specific closed interval given 2 to 5, period. Now remember, I need the y values of the endpoints, so I'm going to declare v of 2 is 0 and v of 5 is 1, 2, 3, 4, 5. V of 5 is about, so we're going to do another approximation. So right here, so that's negative 1, 2, 3, I'll call it negative 3.5, period. So now I have the endpoint y values, and I have to ask myself, is negative e, which we said is approximately negative 2.178, blah, 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 is that between? And it is. So that's what I'm going to declare. So I'm going to say negative 3.5 is less than negative e, which is less than 0. And now I'm going to make my declaration. Therefore, and I'm going to do some copying the prompt. Therefore, comma, there must be a value c, just copying the prompt, where v of c is equal to negative e. Done. I think that's all. Let me make sure. Yep, that's just more practice. So hope that helps. I'm going to make a video hopefully for the second test review and maybe even for some test prep items.